Welcome everyone. In this video lecture, we will think about the why impedance in frequency domain for capacitor, that is the impedance function Z C subscript C S is 1 by SC, inductor ZLS is equals to SL, and resistor ZRS is R. Okay. So why impedance of a capacitor is 1 by SC, impedance of inductor is SL, and resistor ZR is R. So that we will cover. So in general we can also write means if there is a capacitor, okay, if I am saying this one is some capacitor, okay, C. So the impedance is in frequency domain will be 1 by SC, and if there is a inductor, okay, then the impedance will be simply our SL, and if there is a resistance, then the impedance is nothing but simply same as that of resistance value. So that we have to think. So the major reason, we can say, the major reason behind this concept, the frequency domain of the impedance function for the capacitor, inductor, and R1 by SC, SL, R, is mainly due to the Laplace transform. If we say in terms of a single word, what is the reason behind it? So we can say Laplace transform. Laplace transform the region. Okay. So that part we will cover in this video. Okay. So before we will start, we have to think about the some basics about the Laplace. Okay. So actually in the design and analysis of any electronic circuits, the Laplace transform is a very useful tool. Okay. So Laplace transform is a very useful tool to analyze any electronic circuit. Okay. And basically we are transforming from the time domain to its frequency domain. Okay. So with this transformation, what we are getting is with the transformation from the using the Laplace transform, we are just analyzing the circuit in terms of algebraically rather than solving differential equation. So this is the thing. So I have already written here the statement that Laplace transform plays an important role to transform the circuit from the time domain to frequency domain. Okay. So basically this Laplace transform is used to transform or plays an important role to transform the circuit from the time domain to frequency domain. Okay. And considered as a useful technique to analyze the electronic circuit. Okay. And it also helps to transform or helps to analyze the circuit algebraically rather than solving differential equation. No need to solve the differential equation. We can analyze the circuit algebraically using the Laplace transform. So why this ZCS is the impedance in 1 by SC and inductor SL, okay, and the impedance for the resistor is R, that we will think with the help of this Laplace transform. Okay, so this is the simple basics that I covered, that Laplace transform. Why Laplace transform? To just transform the time domain to frequency domain, and it is a very useful technique to analyze the electronic circuit algebraically rather than solving the differential equation. So now one more basic equation that I think many of you know, but I have to write the Laplace transform of any function, say ft, is in general we can write equals to fs equals to 0 to infinity ft e to power minus st dt. Okay, this is very useful formula for the Laplace transform, where this fs, we can say this fs I am writing the transformed function in frequency domain. Transformed function in frequency domain. Okay, basically there is a time domain function, time domain function ft is transformed to its frequency domain, and the term s is called our Laplace transform operator. Laplace transform operator or sometimes it is say the complex frequency variable, complex frequency, okay, variable. Okay, so this is also very important formula. We can say this formula is very useful. Okay, clear. So now we will go for the fundamental, that the question, our question, why impedance is written like this. So for this purpose, I want to just make a table. Okay, so but first I'm just, okay, so I'm just making a table. Okay, so first with here rectangles. Okay, and then you have to one for the, okay, you can take some more space, one for the capacitor, then take one for inductor. Okay, so okay, so here I'm writing the capacitor. Okay, capacitor. Okay, here I'm writing inductor and resistor. Okay, and then after, what I am doing, I am just drawing the cir- simple circuit symbol, a symbol of the capacitor, that is our C L R. Okay, so this one is basically your C L. Right now I'm writing C L and R. Okay, so now here we have to go for the, okay, one more. Okay, so if there is a capacitor and I am saying the current in the capacitor in the time domain is ICT. Okay, ICT. So as we know, in time domain expression for the ICT can be written as C dV by dt. Yes or no? The expression for the capacitor I am doing here. If there is a capacitor C, okay, so we know two expression, Q equals to CV and Q equals to IT. So CV equals to IT. This is just the means. So I see the capacitor current can be written as C dV by dt. Okay, this is the trick to remember the current in the capacitor in the time domain will be like this. Okay, we can write this one as a time domain expression. Okay, is it okay now? Now for the this one is our frequency domain. So now for the, if we want to convert this one to its corresponding frequency domain, so we have to go for the Laplace transform. Okay, so ICT Laplace transform, we have to go for the Laplace transform. So we can write as IS. Okay, for the current IS, and C will be the constant term, and dVt by is our SIS minus I0. Okay, because see, the Laplace transform that you have to know, f dash t is s times of fs minus f0. But here we have to consider our initial condition 0, so we can make it 0. So we can write I s equals to s c I s. Okay, and then after what we can write, sorry, this should be vs. Okay, sorry, there is a mistake that I did. Sorry. Okay, means I is, sorry, is is our c times of v of s into s minus v of 0. Okay, by keeping the initial condition 0, we have to make it 0. So one can write c s into vs. Okay, so we can also one more line, means just like we can write, then if we find vs upon is is nothing but simply impedance function for the capacitor. Okay, as a function of s is nothing but simply 1 by sc. Is it okay or no? Means first we have written in terms of corresponding time domain, then we have written in terms of frequency domain by keeping initial condition 0. So this will be like this. So the impedance 1 vs by is 1 by sc. So our function will be 1 by sc. So this is the way, means how to, I'm saying the frequency domain impedance value will be 1 by sc. The same thing we will do for the inductor. For inductor, what we can say, for inductor we have to know the voltage across the inductor, that is our plus of minus this VLT. As a function of t, we can say VLT is nothing but simply L DIL by dt. Okay, this one is the function, means how it is coming, it is coming from the flux is Li. Okay, in general, and this flux is v times of dt. So Li, this is the trick, means how to remember. So di we can write. Okay, d, okay, L di we can write v dt L di. So di by dt. Okay, so VL. Okay, that you can write this. So this one is simply VL. So VL equals to L DIL by dt. Okay, is it okay? Means simply we have written this VL. Okay, just by using this expression phi Li VL dt LDA. So this one is it. Now again we have to go for the frequency domain. So this one is the differentiation part. So we have to go for the Laplace transform. So if we go for the Laplace transform, what we can write, this one is a VLS. Okay, frequency domain. The time domain is converted to frequency domain. So VLS, then L as it is IL. So it should be H times of IS minus I 0 by keeping initial condition 0 in this case. So one can write VLS equals to SL into IS. Okay, then if we write VLS upon IS is nothing but simply the impedance of the corresponding inductor, that is our ZLS, is S times of SL. So here we can say this one is the basically the proof. We can say the impedance function for the inductor is S times of L. Okay, clear this one. So now for the resistance. So for the resistance, okay, if there is some resistance, the current is flowing. Okay, so simply what we know, V equals to V equals to I R. Okay, So R is constant. So this Vs Is. Okay. So this one is in time domain. So for example, one more line, that is a Vt, and the current is a time varying function like this R. So the frequency component will be simply Vs Is into R. So we can write as Vs by Is is simply ZRs is nothing but simply same the resistance value, that is our R. Okay. So like that we can do. So this is the concept behind. Then sometimes it is little bit confusing that why this capacitor is 1 by SC, inductor SL, and resistor same, no change. Okay, so this is the reason. Okay, means we have to think about the Laplace transform. So basically Laplace transform the time domain to its frequency domain, and Laplace transform is a very useful technique for the design and analysis of any electronic circuits, okay, which transform the time domain to its corresponding frequency domain. Using this transformation, the analysis of the circuit can be conducted algebraically rather than by solving differential equation. So this is the reason why the inductance value for the capacitance or impedance in frequency domain for the capacitance are 1 by SC, okay, and for the inductor SL, and for the resistance simply R. So this is the concept behind all this thing, and this one is the frequency domain impedance function or impedance function in the frequency domain. So this is all about this video lecture. So thank you for watching this video. Thank you.